Hello, and welcome back to the second in a series of programming in assembly language on the Atari 8-bit computer using the Mac 65 assembler editor cartridge. First, I want to thank people for all the support the first video got. As of today, it hasn't even been up a week, and it's already got over 750 views, so I consider that quite successful for my modest goals. So thank you. I want to stress that you do not have to have watched the action series that I did on programming on the Atari in action. For this series, I'm going to assume you didn't watch any of them. But I do assume in all this video and all the rest to come that you've watched the previous videos in this series, because I won't repeat things I've done in earlier assembly tutorials. So today's video, I want to cover three things. I want to talk about the rest of the Mac 65 editor commands. In fact, we're going to go over all 21 of them today. Hopefully it won't be that long. We're going to take a little brief introduction to the DDT debugging tool that's built into Mac 65. And the last thing I want to do is actually write a demo program in assembly language. Now, in almost all the different 6502 assembly books and even the Tom Hudson series in analog magazines, the first machine language demo always seems to be, here's how we add two numbers together. But this is the Atari, right? We don't want to, I don't want to teach assembly to add two numbers together. We want to do stuff on the screen. So we're actually going to do the other famous computer demo program, the Hello World demo. And that may sound sort of trivial, but it involves writing onto the screen in assembly language. And that's something that we're going to be doing quite a bit going forward, putting stuff on the screen. So this will just be a quick introduction to that. And given the power of Mac 65, we're going to write that Hello World demo program, and it's going to take under 30 bytes of assembly code to do it. So that's going to be thank you to some of the power of Mac 65. But before we get to the programming part, I do want to cover the commands. I think it's important that you understand this video series is not just about learning assembly language, but also learning how to get the most out of this Mac 65 cartridge. It's not about Atari Assembler Editor or EASM or any of the other development environments out there for doing assembly language for 6502 or on the Atari. It's Mac 65. It's super powerful for doing assembly, and I want you to get the most out of it. So we're going to go over all the editor commands today. There's only 21. So I think I mentioned last time that text, right, is a useless one. So that one we're not going to talk about, but there's one that's even more useless, and that is the by command. And all that does is either put you in memo pad if you're on a 400, 800, or it puts you into the self-test mode if you have an XL or XE. So, what anybody would find use for that command, I don't know, but it's there, right? All right. Last time I talked about bsave, which took a every time I hit reset, it always throws me back to the top level directory. But and you give it a less than sign and two memory addresses. So last time it started at 680 to 689, And this is one of the rare cases where Mac65 expects hexadecimal code but will not require the $sign for it. So that's how bsave works. And last time we did save our program that way, and it did start at hex location 680. We're going to take a real quick dive into DDT for 1 second. So let me adjust the screen a little, sorry. Just want to make sure you're getting the whole screen. Anyway, DDT, you can go to a memory location with two commands, either the asterisk you can use, or E for examine memory, and then you can put in the memory location you want to go to. And as you see, there's just some junk here, F78C, blah, blah, blah. It's not our program that we wrote, so this is not the stuff that we wrote last time. So we are going to load that using bload. And I think I called it reset. Now, I do not have to specify addresses here because it's just reading the bytes off of the disk, and then it will store them in memory based on what you put into the memory code that you put on the file that you saved. So now if I go back to DDT and I go to 680, now you can see this is the code that we wrote last week. Push the accumulator on the stack, load the accumulator, store at a value. The thing I want to show about bload, though, is it's just loading into memory, the memory locations. It takes your object code that you wrote and loads it into memory. It doesn't load your assembly listing. So your assembly listing is not entered, just the actual bytes that you wrote to the memory locations you wrote them to. So note that about bload. It does not require addresses, but it doesn't also load your assembly code. All right, so we did this. So we are going to load, just so we have something to play with for these examples. So now we do have some code in there. So, and we talked about assembling that code using the assemble command last time. So that will assemble our code that we wrote. But I didn't go into the full detail of the assemble command, which I will now. So the assemble command actually takes 4 parameters or input arguments separated by commas, but they're all optional. All 4 are optional. So obviously I didn't put any when I typed this, so there's none there. But the 4 parameters are, the first one is the source. So the first parameter is, where could I get the source? Where can I get the source from? The second one is, where can I list it to? The third one is, where do I want object code to go? So what this version of assemble says is, I'm going to take that program off the disk. I'm going to do the listing to the printer, and then I'm going to write the object file, not to memory. I'm going to write it right out to the disk. Now, the defaults for all of these is the default if you don't list the first one, it's going to assemble your code from what's in memory. If you don't have the second, it will list it to the screen. And if you don't have the third, it will assemble your code to memory if you have that opt obj that you see up there on line 110. So this will actually work. It'll assemble it. Oh, I guess it doesn't work. So we could say, oh, we could do this. I bet that works. No. All right, I'm going to have to look that up. Thought I had that correct. Source list output. Oh, I said there was four parameters. You don't have to worry about the fourth one ever. So we've got assemble, bsave, bload, by we talked about, DDT we showed. There is a delete command, which will let you specify either a single number, a line number to delete, or lets you specify a range of line numbers to delete. Now, this version is kind of useless to me, or seems useless to me, because, right, I could do the same thing by just typing this, right? So delete 100 would be the same thing as if I just typed 100. It would wipe out, whatever's on that line, right? So line 100 is gone. That's the same as right. So I don't know what delete 100, I don't know what the single one would be. It's more useful when you're going to delete a block of lines. I guess all the lines have to exist. Yeah, so all the lines have to exist. So there you go. Even I learned something. All right. So we have load, we have save, we have list, and we have enter. So there is a way to say if I do it like this, it will load it in. And unlike Atari Basic, this enter command will wipe out whatever's in memory and replace it. So if I had some other, this is identical to the code that's there, but if I, actually, it's not, right? So this was identical to the code that was there, but if it was different code, it would wipe it out. You can do this. And then put comma N, which says, hey, merge this without wiping out what's in memory. So the default for basic is, for an enter, is actually merged. But for Mac65, the default is not merged. The default is to overwrite. So if you want to merge listed code, you want to use a comma N. You can also use, just one second, I'm going to do this to make things go faster. You can also use /A to enter unnumbered text. How would you get unnumbered text? There's actually a print command which prints your code without line numbers. So if you wanted to get your object code without line numbers, you could do print. And you could also we'll just call it that. So new, of course, will wipe out what's in memory, along with delete all the line numbers. Now what happens if I use that enter command, and this has no line numbers, comma A for unnumbered text. I don't know why A is not append here, but you can see that it takes the unnumbered text and it auto line numbers it for you. So it starts at line 10 and increments by 10. So if you don't have line numbers, it'll give you line numbers. But this, if you enter with the A to load in unnumbered text, it will always wipe out what's in memory. So it will never save. You can't merge and load unnumbered text at the same time. You can do list, right? The same way as you do list in BASIC. You can say just list line 30. You can say list 30, everything from 30 to 40, inclusive. You can also do a load. And here, go figure, right? This will, this of course is the load command, so it only works on those tokenized files. But the default in BASIC, if you do a load, is the opposite, right? The opposite of enter. Enter will merge the code in BASIC, and load will wipe it out in BASIC. In Mac65, the enter will wipe it out, and you need the M for merge. But for load, they didn't call it merge, they called it append. And if you have duplicate line numbers on your saved code with what's in memory, the code that you're loading in will overwrite anything that's there. Okay, size we talked about. So this shows the absolute bottom of memory. This shows from 2300 to 2558 is what Mac65 is using to hold the program. So Mac65 is using this 258 bytes of hex. And again, remember this command, the question mark 2558. So Mac65 is using up to 9560 is the the low part of memory. And as we write more code, Max 65 will, keep making that number bigger. 2558 gets bigger. You can also use this command, low mem. This is going to wipe out my program, by the way. If you use low mem to change where low memory is, it will wipe out anything you have in memory because it's resetting memory. So, oh, and I guess it only takes low mem only takes hex numbers, and this is another case where sometimes it wants you to put in a $sign. This is a time when it doesn't. So now if I do the size command, you'll see the lower part of memory here is now 3000, and Max 65 is using up to 200. And then if I load, you can see the low memory goes from 3000 to 322C with what Max 65 is using. So it gives me less free memory in between where Max 65 is starting and where, or of the amount of memory that Max 65 is using to hold your code and anything else that it's using, and the top of memory. So you can use that low mem to like, okay, now since I set low mem to 3000 and Max 65's using that as the low memory, I could stick some stuff in between, right? I could stick some stuff under 3000 to store some data if I wanted to hide it in there. All right. Let's do this again. And remember, this is the unnumbered code. Wow. Oh, probably because I reset low mem. I guess it doesn't like that. All right. I'm learning with you today. How's that? Okay, I should have tested all these. I guess so. All right, that's going to be subject for a future video. What's going on with the print and the list? The next thing I'm going to talk about, I talked about num last time. That is to set up automatic numbering. So you can set the lowest part where you want your memory or your numbering to start. So I could say I'm going to start it at 180 and I'm going to increment it by 10. So now I could, 190. So this will do some, right? That RTS is not a code. To get out of this, you just hit the break key. So now I can use the REN as renumber, and again, it just tells you where to start, where you want to start, and how much you want to increment it by. So I could change this to 20. Oh, the starting line number and the ending line number. So now you see it changed it from incrementing it by 10 to incrementing it by 20. So the first line number is where I want it to start renumbering, and this is how much I want each step to be when I renumbered it. The default, if you don't do anything, is to go by 100, increment by 100. Start at 10 and increment by 100. So that's not that good. We'll start by 110. Okay, so, and then I don't want those lines at the end, so I can just do that. All right, so we've talked about everything except the last two commands that I'm going to go over, and that is find and replace. So there actually is a find and replace, and on this program, that's not going to be so. You basically put what you want to find in between what they call two delimiters. And these could be any character you want. I mean, I use backslashes most of the time, but if you wanted to find something that included a backslash, you could use, you know, exclamation points. You can use whatever you want. And what this does is it gives me the first line number that it has the string that I'm looking for. If I say and put a comma A after it, that means find all references to that string. The interesting thing is it will ignore comments. Also, you can say and say, I only want to look within a certain subset of lines. So in this case, I'm just searching for 100 to 140. I can also use, find will ignore comments. So stuff that's in comments, find won't find it. So it only works on your assembly code. All right. And the last one is replace. And that works kind of similar. If I do it like this, it only changes the first one. Helps if I get the right string, right? I'm thinking. And if I put an A after that, right? So the first thing is what is the old, and the second one is what is the new. If I put an A after that, it changes all of them. And the last way you can use this is with a Q, which stands for query. And what it says is it will prompt you. Do you want to change this one? Yes. Do you want to prompt this one? No. And you see it only changed the first one. All right. We're going to start writing our a half hour in, and I haven't even gotten to writing the program yet. All right, so I was going to do a little intro to DDT, but I think I am just going to write the hello program, hello world program, and hopefully that will be what we're going to do for tonight. So I always start at 100 because if you use tens, then when you get to 100, it goes out one digit. This way I remember I have the right number of spaces. So I use comments quite a bit, and I'm going to talk more about comments in a minute, about the different ways you can comment them. So last time we were starting out in starting our program down in page 6, but we got plenty of memory to play with, and this is only going to take less than 30 bytes. So we're going to start our program at 5,000. And what we're going to talk about today is, and remember, right, if I have one space, it's going to be a label or comment. 2 spaces, it's going to be a directive or an instruction. Right now, I'm going to make this a comment. So remember, what this line does is, if I don't have this in a Mac65 program listing, this compiler directive, it will not compile to memory. It'll just tell you, it'll compile, but it won't go to memory. That way, you're not have to worry about things totally messing up. All right, our program is going to start here, and we're going to use a label that we'll call string. And I'm going to show you a special Mac65 directive, which is called byte. What byte lets us do is enter program data, or let us enter bytes into memory as they are. We're telling the computer, don't try to interpret these bytes as instructions. They're just bytes I want to put in there. You can do that by, putting them in 1 byte at a time, etc. But Mac65 will also let you do this. So this line says to Mac65, hey, byte says take these characters within the quotes and just insert them right into memory. So I'm going to use a label here called start, and that indicates to me where this program starts. You'll see why that's useful. I'm just going to explain as we go, and then I'll probably dive into this program way more deep in the next video. So the first instruction we're going to do is load the Y register with 0. All right, so I do have to go to DDT. I'm sorry this video is going to be long, but that's what you get when you try to write assembly programming on the fly. All right. DDT, in addition to being a debugging tool, is also super handy for giving us a peek at the 6502 registers. So the chip that we're programming, the 6502 inside your computer, can do some things. It interprets your instructions and it moves memory around. And there are 6 registers of interest to us. And DDT will show us all of these registers. A register is either 1 byte or 2 bytes, and it's kind of like a memory location, that holds 1 byte of data or 2 bytes of data, but you can't peek or poke it. It's not actually in memory. It's just in this register on the 6502 chip. You have the accumulator. This is like the main Grand Central Station of the 6502. Almost all the data moving through the 6502, in or out, goes through the accumulator. The X and Y registers are usually used as counters, or sometimes they'll temporarily hold data. If you think of the accumulator as a cat in the hat, then X and Y register are like thing 1 and thing 2. They're helpers that help us do things. We're going to use that Y register as a counter. So that's what we're going to use the Y register today for. The accumulator is going to be doing all the heavy work, but the Y register is going to be our counter to count the number of letters that we want to write on the screen. The other 3 registers that are here are the stack pointer. We'll talk about that later. This is the status register that has some flags. We'll talk about that later. And this is a program counter that says, where would this where would your computer start running its code at this particular moment? So once I exit DDT, I guess, it goes to BEFC or something. So probably in the Mac 65 cartridge somewhere. But we can set that to whatever. But the important parts today is, all we're going to work with today is the accumulator and the Y register as a counter. All right. So what I'm doing is I'm loading the Y register. So LD is load, and I'm loading the Y register. And that # hashtag means I'm loading it with the literal value of 0. So I am sticking a 0 into the Y register right there. And now I've basically, it's like for Y equals 0 to some number. So I'm going to loop. So I'm going to create a label called loop. And I'm going to load into the accumulator. All right, so what's going on here? So this is just a label. This is an instruction. It says load into the accumulator. And if I, this comma Y, this is a memory address. And Mac 65 knows that the memory address of string is up where I put this label. So it says go to the memory address right now, and then it's going to add the counter to the memory address. In this case, the counter is 0. So it's going to look at the first character in our string, the H. So what that does is it takes the character H and it puts it into the accumulator. Now, I'm going to store the value that's in the accumulator, and you're just going to have to trust me on this one right now. But if I look up in if I have, here's Day-Ray Atari. If you look at location 88 and 89 or 58 and 59 in hex, that is the lowest address of screen memory corresponding to the upper left corner of the screen. And what that says is, putting this in parentheses says, I'm only giving you 1 byte here, and let's make that hex, because we should all be getting used to hex. But as you can see in the, right in here, it's you can look them up and go in between the two. So what this is saying is I loaded the H from Hello World into the accumulator, and then I'm storing it at the address at 58 and 59 in hex, plus this. So right now, let's say screen memory is 40,000. Then it would say, okay, I'm going to look in here for the address. The address is 40,000, and I'm going to add 0 to that. So I'm going to take that H that's in the accumulator and stick it in that memory at 40,000 plus 0. Let's do it this way. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters in our string. As I'm going to go through this loop, this is not copy, it's compare Y. So it says compare what's in the Y register right now, which is 0, to the number 12. So this always means the hashtag /# does not mean memory location. It means use this actual number, 12, which is also B. So get used to those. And then I'm going to do a branch if equal to the end of my program. So what I'm going to do is Y starts at 0, 1, 2, 3, 4. When it gets to 12, it's going to say, hey, is Y equal to 12? Yes. Then I'm going to branch when Y is equal to 12, branch on equal to the label for end. Now I haven't written a label for end yet. If you remember, in Action is a one-pass compiler, so I couldn't write end here and then define end later on in Action. I would have to write end up here if I wanted to branch to it, because Action doesn't have forward references, but Mac 65 does. Now, if I get to line 210, which is not end, then I must have failed this equal check and drop down. So in that case, I'm going to increment Y. So I'm going to raise the value of Y from 0 to 1. And then jump back to the top of the loop, where now at the loop, so I increase Y to 1. Now I'm going to go to the string +1. So I'm going to grab the E. Then I'm going to store it at the screen memory +1 and put the E there. And then I'm going to check, is 1 equal to 12? No. So I'm going to increment Y to 2 and then jump to the top of the loop, etc., etc. So now here's where I would put my end. So let's talk super quick about comments. There's 3 ways you could kind of comment. You can you could put a comment on the same line. On 40 columns, this messes up your display, but if you print it to a printer, it's 80 characters width, so this would come out nice. You can put comments on the same line here, like this. You could add your comment in between lines. Usually what I like to do is what we have up here at the top is put all my comments up in the top. So I would put something before start that talks about what this whole loop does. I would have a block of comments up there. And the reason being then it just makes the listing come out nicer. So let's try to assemble this. And remember, this is commented out, so it won't go to memory. So that compiled cleanly. And here you can see some values for our labels. So our string would be at memory location and this is why you have that commented out. Right? This is why you comment out OptoBJ so it doesn't compile to memory. Because then sometimes you may forget, like, oh, this is one of the places where Mac65 wants a Mac65 does want a $. So see why I knew I was looking at this isn't started at 5,000. Why is this here? And then I knew that this was the reason. Super common mistake. I'd like to say I did it on purpose. But that's why you assemble with OptoBJ turned off so you don't crash your computer. Now everything looks right? So like string starts at hex 5000, which is where I expected it to be. The actual start of my program's at 5000C, not at 5000. And the end of my program's at 1B. So that's 16 plus 12, that's 28 bytes. So remember I said we could write this in 28 bytes. So let's now that we got a good compile, let's go here. And assemble it. And now if I go to DDT and I examine 5000, well, you're going to see some stuff here, right? But this is not code, right? Doesn't even know this is code. But remember at 5000, this is my string here, not the program. So I don't expect this to be program code. If you remember, my program actually starts at C. Now that looks like what we did, right? Load the Y register with 0, load the accumulator into, or load the accumulator with the value from the first byte in our string plus Y, store it at screen memory plus Y, compare, branch if not equal, or branch if equal, and you see here, DDT tells us, hey, I don't have labels in DDT, so I'll tell you that if this is true, it's going to branch down to 501B, which is our return to subroutine. And then you'll see that everything after that, right, is all empty code. So let's save this first. And then we're going to do B save. All right. And again, here's where this information comes in handy for me. So even though my program starts here at 5000C, I need to capture the data that has my string in it, and I have to capture it all the way to the end. So when I save this object file, I need to say, hey, capture all the data from 5000 to 501B. Now remember, the program does not start at 5000. Even though we started using memory at 5000, the program actually starts at 5000C. So to run it, I have to tell the computer, hey, don't start at 5000 because that's just string data there. Oh, so that didn't turn out right. But this one I did plan in advance, so it turns out that if you did watch the action series, but you don't need to know that to have watched it, to know this bit that I'm about to tell you, is this is putting ASCII codes into memory. But the screen uses a different internal code. Now, in action, I actually had to write a routine to translate ASCII code into screen code. But Mac65 actually has a feature that does it for us, and that is called SByte. So what SByte does is say, hey, don't interpret this as a ASCII code, but interpret it as screen code. So we're going to assemble that to memory. We're going to save it to make sure we captured the change. B save it so we can run it. And there we go, the hello world in 28 bytes of assembly code. We're going to dig into that more in the next video. One cool thing that we're going to do is with DDT, we can go to the start of our program at 5000C. And you see it changed the program counter to 5000C. That's where our program starts. And if you use the option key on the Atari here with DDT, it will start executing these functions one by one. So the first thing says load the Y register with 0. That's not really going to show much to us right now. Then it's going to say, hey, load the accumulator with the screen byte for the capital H that it can find up above there. So you can see the accumulator changed to 28. So if I go look at 5000, right, which is where our thing, there's a 28. So that's the 28 that got put into the accumulator. See, this program counter's at 5011. That didn't change. And then we're going to do option to store this in the screen memory. And then if you want to take a peek at what's happening on the screen, you hit the select key. And you see up here, it started putting the H for hello world. And then select will take you back into DDT. It's going to compare Y which is 0 with 12. Then if that was those two values, 0 and 12, were equal, we would jump down here to 501B, but it's not true, so it's going to go down here and increment Y from 0 to 1. Then we're going to jump back up to 5000E and start the whole thing over again. So now we're going to go to that byte of our string, but now we're adding 1 to it. So instead of a 28, it's going to get some new value, 65. It's going to store that in screen memory. I can go look with select. There's the E from Hello World. And then basically I can step through this all the way to the end. But that's almost an hour-long video that I've got so far. So, to sum up, we covered all the rest of the Mag65 commands. We took a kind of tiny peek at DDT, and we wrote the whole world Hello World demo in 28 bytes of assembly language. So, again, just real quick, this first column, when you do the assembly, this first column is the memory addresses. So you can see that 5000 up to 5012, this is our string bytes going into memory. The first instruction starts here. And then these are the machine language bytes in the memory. We could look at that in DDT. And I'm going to come back and explain in more detail all about this magical beast here and some other things. There's no test at the end about, do you know all the different addressing modes? I'm just going to teach you the ones that you should know as you come across them. Sorry, I needed a drink. I'm going to teach you the ones you should know as we need them. And we'll go into this in more detail in the next video, which hopefully will not be an hour long. So thank you. Bye.